Okay, so it's 11 o'clock. Let's get started. Thank you very much for being here. We've gone from a cloud presentation to a deep microarchitecture one. Hopefully the audience is still interested. And today I'm going to talk about the how you build an out-of-order RISC-V vector unit. The program committee insisted a lot that we try to tell you things that you can learn. So not only we'll tell you about the product we've done, but what are the difficulties you'll encounter if you try to do the same, right? And this is the outline of my talk. This was my second title. I decided not to put it, RISC-V vectors and out of order. I call it a tense friendship. There's a lot of things you have to do if you want to do out of order and vectors together in the microarchitecture. So there's quite a bit of extra work from just an in-order vector unit. And I'll go through these one by one, so I won't bore you reading them now. The one-line summary is don't worry about it. I mean, if you don't leave the room thinking, oh, I heard a guy saying it couldn't be done. Quite the contrary, it can be done. We've done it. But there's a lot of work in mixing vectors and out of order and renaming. So let's get right into it in case someone is not familiar with RISC-V vectors. There's the very basic two-instruction program using RISC-V vectors. Let's focus on the second instruction. Let's see if I can learn to use that. Yeah, the VAdd, okay. So the VAdd says I want to add two of the vector registers of the ISA, V5 and V6, and I want to put the result in V7. All of you guys knew that, right? The instruction before that is VSet VLI, and if you have not been reading the spec in detail, maybe you don't know it. It tells the machine how to interpret the VAdd. So it tells three things, right? Let's start at that E64 thing in there. That E64 says the next instruction coming, and in fact all the coming vector instructions actually should operate on 64-bit elements, right? The M1 we'll leave for later. That's the Elmol multiplier, and we'll talk about it. And the X8 tells the machine how many elements inside the vector you actually want to operate on. So if X8 contains the number 5, it means that you want to operate on 5 elements inside the vector only, right? And so, just to get you acquainted with the pictures in the presentation, this would be a visual representation. There's, I've chosen to have 5 12-bit vectors, which are pretty common in the industry. And because in the instruction we see the E64, it means that the 5 12 bits are broken down into 64-bit quantities. Therefore, there are 8 elements in the vector. 5 12 divided by 8. By 64, that's 8, right? So V5 is a vector, V6 is a vector, and the VAdd instruction says, please add me each one of those 8 elements together and produce the result and put it in V7. Okay, you all guys, you knew that, but I needed to fill up the first minutes so people would be able to come into the room. So let's focus on the first instruction, VSet VLI, right? If VSet VLI, if that X8 register that you can read over there contains the number 5, what it means is it says that, okay, yeah, there's V5, there's V6, I just shown this picture, but hey, I actually want you to please only add the first 5 elements. I'm starting at the bottom of the vector. And therefore, you have to put me the 5 results into V7, and the question is what happens with the other 3 boxes that are gray colored, right? The spec gives you 2 options, one that's good for in order and one that's very bad for out of order, right? The spec says you can either fill those boxes with ones. That's fantastic for out of order, but unfortunately the spec also says, oh, but if the programmer chooses, then you have to keep in V7 the previous value that was there, right? And so how is that a problem if you decide to build an out of order machine? Well, if you do an out of order machine, a full out of order, you'll very, very likely, 99% sure, you'll choose to do renaming. And renaming is a technique that takes the registers, the virtual registers, and remaps them into physical registers. So, the text in the middle of the slide shows you, okay, 3 instructions, and then to the right in this, whatever, purple color is the rename register. So let's read the second VAdd instruction. It says, I'm going to use V5, V6, and write into V7. The hardware in an out-of-order renaming machine says, well, you're not going to write to V7. V7 really doesn't exist. There's something we call vector physical 11, and that's where you're going to write. And I want you to note that the second instruction, the second VAdd, also writes to V7. It's a bit silly as a program, but it's completely legal. And the second instruction, the renamer will say, oh, you want to write also to V7? No problem. You should write into physical 29. So we have two instructions writing into V7 in the machine at the same time. One is going to write into physical 11. The other one is going to write into physical 29. So where's the problem with out of order renaming and the vector spec? Well, the problem is, and I made the example a little bit longer just to make it more interesting. So we set the VLI to 8. That's an illegal assembly syntax, but I hope you'll forgive me. Then we do a VAdd. Then we say, now I want to add only 5 elements, and we do a VAdd again, right? How's that going to work? Okay, the first VAdd is going to write the whole thing, 8 elements, A, B, C, D, E, F, G, H, into the register, no problems, into physical 11. The second one is going to write 5 elements, right, in yellow, into VP29. And the problem you have as a microarchitecture designer now is like, oops, you need to fill in those 3 gray boxes with question marks with some value. Which value? Precisely F, G, and H. That's what the spec says you have to do. And that means that in an order machine, that's a no-brainer. There's only one V7. You just write there, no problem. So, in order people should not be in the room, right? On out of order, you got to get F, G, and H from somewhere. So you can either insert a copy UOP and read from VP11 and copy into VP29, or maybe you can make VP11 a source of your instructions, and those of you that are paying close attention will say, hey, but there's already VP11 in your slide, so why are you even complaining? Well, that's my example, but there are many cases where that destination is not going to be a source. So you as a machine designer, you have to now say, oops, now my destination data becomes a source. So my 3-source out-of-order machine becomes a 4 or 5 or 6, as we'll discuss later, and I have to do more wake-ups, and it's more complexity, right? Now, this gets even worse for the people that enjoy long vectors, right? Most of the room probably are familiar with AVX 512 and ARM SVE. It's also around the 512 mark, but if you go beyond that, 2,000 bits, 4,000 bits, and beyond, then this tail problem becomes really irritating, right? You've been doing this vector work in big vectors, you're very happy, and on the last iteration of the loop, this silly vector length comes around, you have a 4,000-bit vector, and VL is set to 128. And so everything between bit 129 all the way to 4,095, you got to fill with something. So you waste computation cycles just to respect the spec. So that's something you'll have to deal with if you decide to do this. Let me add more to the problem, another reminder of the spec. One thing that good vector ISAs have is operating under mask, and obviously RISC-V does have operation under mask, of course. And so now I'm making the VAdd a little bit more complicated. I'm adding these 3 letters there that say the VAdd under control of V0.T. In the spec that says, well, I'm going to add only those elements in V5 and V6 that are indicated by the mask, and the mask is located in V0, actually located in the low order bits of V0, and I put you an example there of the mask. So if we apply this mask to V5 and V6, we would have V5, V6. Now V0 becomes an input to this instruction. That's another source that you maybe will need to rename, and we'll get to that in a second. And V0 is the one that says, okay, if you look at the bit pattern, you see 1, 0, 1, 0, 1, 0, and that says that only the odd elements have to be added, as you see in the representation. So only those guys will get added, and the guys in gray should contain what? Again, the previous value. Yes, there's a setting that says you can wipe them out and put ones, but unfortunately there's a setting that says, no, you got to preserve the old value. So both the vector length and the vector mask cause this problem that now the old value of V7 becomes a source to the instruction, right? To add to this, did you notice the bit layout? If you were paying attention, you noticed that I put X's everywhere in that V0. The top bits of V0 for this operation don't matter, but the bottom bits actually are the ones that set the mask. So what that means is that the bottom bits are being sent, and I'll show that more in a floor plan way, are being sent from the lower bits of V0 and have to reach the functional units that are producing those results and tell them, hey, I know you were adding something, but please don't write it back to the register file. Turn that enable off, because the mask says we shouldn't be doing this, right? So that's one thing. And why is that even a problem, or why is that a problem more for out of order than for in order? The typical vector machine you'll build is composed of lanes. So a lane is a big floor plan thing. It's not small. So it's a big chunk of logic. It contains a chunk of your vector register file and probably an FMA, an integer, maybe even a divider, cross-lane logic. So that lane, you choose how many lanes you do in your implementation. The one we've done has 8 lanes, and each lane processes up to 64 bits. So our data path, we've decided it's 512 bits wide, right? You can do bigger, smaller, no problem. But you're likely to do an implementation like that, because once you design the vector unit, you quickly realize, oh, wow, that's great. All the lanes are the same. So I'm just going to do that and replicate multiple times. So if I map this lane idea, now I'm trying to get you to floor plan thinking, right, into this abstract operation of the instructions, I put underneath each of the elements the lane where they are located. So, the guys on the far right of the PowerPoint are in lane 0, then lane 1, and so forth. So physically, lane 0 and lane 5 are not likely to be close by. They're going to be, not far away, but not exactly, it's probably, you'll probably need a high-level metal to talk from one to the other. So what this means is that because the bits are all at the bottom, you'll need to actually distribute those bits to all the lanes, which is kind of annoying, right? Let me say some more about the mask, a little bit more of a primer. How do you create a mask in RISC-V vectors? Well, you compare 2 registers, V set lower than V5, V6 is going to take the 2 registers, going to compare each element one by one, and it's going to generate a bit mask. Where does the bit mask go? Oops, the bit mask goes from every lane down to lane 0. And for those that like to nitpick, there's details here. If Elmol is bigger, in certain cases, it could go to lane 0 and lane 1 and maybe more, but good enough for the example, right? So basically, I'm just boring you with these wires to show you that there's like a bunch of wires going from every lane to lane 0 for the masks, and from lane 0 to every lane for the mask again. Now, what's the difference between in order and out of order, which is what the talk is about? If you were doing in order, what the choice you would make is probably very likely. You would make a shadow copy of that vector mask, right? You would say, okay, every time anyone writes V0, this is easy in an in-order machine, you know what, I'm going to keep a copy of those bits in a flip-flop. And you'll probably let actually those flip-flops be at the top level of your RTL, of that vector unit, and you let the tool just do the wires, and it's going to kind of work. So you're going to, whenever you write V0, you're going to write into those flip-flops, shadow copy of V0, and whenever you use the mask, you're going to read from the flip-flops. In out of order, we're out of luck, because how many V0s do we have in an outer machine? Well, actually many. If you have multiple instructions that write V0, be it because they really intend to create multiple masks, because the compiler was just sloppy, now we have 5, 6, 7, 8. You tell me, how many copies of V0 can we have in the machine? So now you're like, oh, gee, that idea, that cool idea in order, which is a shadow copy, now I need 5 shadow copies, 6 shadow copies, or 8 shadow copies. And at that point, it's not so attractive, because now not only you have the wiring, but you have a muxing, and it's all kind of ugly, right? So yeah, it's buildable. We've done it, but again, it's going to cost you some to decide how you do that, right? Okay, more stuff. How am I doing on time? Okay, so vector state. The other thing you have to keep track in the vector machine, if it wasn't obvious up to this point, is all the little state that actually controls how one vector instruction operates. And I hope you already knew that, but I'm just going to go through it again. So that my example, my friend, the VAT here, V4, V8, V12, with the mask, what do we have? We have 2 sources, V8 and V12. We have the mask, that's 3 sources. So if you wanted to do full out of order Intel style, that's 3 wake up cams just for those things, right? But we also need the vector length. You need to know how many elements this one guy is going to do, because maybe you have VAT, change VL, VAT, change VL again, VAT, and change VL again. Do you want to support full out of order in your microarchitecture? Of course, there are options here, but you can choose that. And you have to remember the SCW. The SCW tells the vector add instruction whether it should be doing 64-bit adds, 32-bit adds, 16 or 8-bit adds, and whatnot, right? So you have to remember that. And you have to remember the Elmol setting, which I haven't got into, but trust me at this point that you do have to remember that. So in a fully out-of-order machine, you do need to track them all. And to just illustrate that, imagine the vset VLI, right, which seems a very innocent instruction. What is it doing? It's doing lots of stuff, right? It's setting VL to the minimum of X8 and max VL. So there's a register there, VL, that you need to now replicate and copy if you're doing out of order. It's setting another thing called V-type. I'm being a little bit sloppy here with naming, but it's putting E64 and M1 there. And so in a way, it's an instruction with 3 destinations, or the way we look at it, it's an instruction with 3 destinations. The actual return data that the vset VL returns, the new VL value that you want to track, and the new V-type value that you want to track. So in a way, the VAT actually doesn't have 2 sources. It has these 2 sources with at least 2 more, one for VL and one for V-type. And if you're familiar, and I'll keep using Intel as an example, but same for all out-of-order machines, if you've designed an out-of-order instruction window, how does it work? You have a bunch of instructions waiting there, and for each instruction times for each source, you have a wake-up cam that says, hey, this source is ready, right? So, you know, just reading the last line that I have on the screen is like, okay, how many wake-up cams do I need for that VAT if I go full way, right? Well, at least 4. One for VP17, one for VP15, one for the VL register, and another one for V-type, right? Now, you can actually take middle positions. You may not go full extreme in this, right? And you could say, well, you know, maybe, hey, Roger, why don't you just gang together VL and V-type? Fair enough. Or why don't you just do other tricks? But I'm trying to highlight, if you wanted to do like the ultimate out-of-order machine, those are sources that you need to consider in your out-of-order window, right? Of course, you can always say, well, when I see a vset VL, I'm going to be really scared. I'm going to stop at the decoder and wait until the machine drains. And that's a valid implementation, but obviously not great performance. Okay, we finally get to Elmol. Elmol, what is Elmol? So first let me just remind those of you that are not so close to the spec. Elmol is a setting in the machine that says the programmer can say, I want my vectors to be twice as big or 4 times as big or 8 times as big. And that's under software control. When the programmer says, I want vectors to be twice as big, what happens is that we group the vectors. So V0 and V1 now become a new entity called V0. V1 disappears from the machine. V2 and V3 become grouped together, and V3 disappears from the machine, right? So you lose logical registers. So the same instruction, VAdd, V4, V8, V12, which looks really innocent when you look at the encoding, actually means 3 different things based on Elmol. Elmol 1, you all know what it means. I want to add V8 and V12. At Elmol 2, if you read the text, it says, well, I want to take V8 and V9 as an entity and add them to V12 and V13 and put the result in V4, V5, right? And I put Elmol 4 there for you. I'm not going to read it, and I left Elmol equal 8, which is legal, as an exercise for those watching this offline, right? So as a renamer, I think you're in charge of the renaming unit in your next design. What do you have to do? When one of those instructions arrives to you, let's take the Elmol 4, let's look at it. What does it mean? It says, okay, I want 8 source registers, you can read them from V8 all the way to V15. And if you're renaming at the individual register level, that means you got to read you got to put 8 rename ports on 8 ports on your rename table, or choose other strategies, right? You know, the immediate request would be, okay, give me 8 read ports to that rename table, and by the way, from the free list, pop 4 free registers so that you can rename V4, V5, V6, and V7, right? There are, of course, alternatives, right? You could think of a renamer that's organized by Elmol, so you may decide that you don't just want a simple, boring, unsorted free list with silly registers in any order. You could say, no, I'm going to try to have my free list organized by groups of 2 or by groups of 4 as the free registers come back. That has some performance implications, but you could do that. Or you could also decide to, go back 35 years, which is totally fine, and break the operation into micro operations, and instead of just dealing with this thing as a big monster, just breaking it into little pieces and dealing each piece one by one. Right? So that's another complication you'll find in your renamer, like you'll have to choose one of these, or maybe a more clever one of the three I mentioned, one of these things in your renamer. Right? But you're not done, right? You're not done by any means, although the time is running up. There are then additional complications. Once you go into Elmol, then there's some instructions that actually cause a lot of trouble. Which are those instructions? The VAD is not especially difficult because it's independent or parallel, right? I'm putting, again, the same code as in the previous slide. But if you think about it, that VAD can be easily broken into two micro operations that just do independent stuff. So not too difficult. But there are a few instructions, reductions and VR gather, and I particularly like the VR gather instruction, so this is not a complaint about it, that actually cross the Elmol boundary so that you cannot see the instruction as 4 independent microbes. It's one gigantic blob of work, right? So let's start with reductions. VSum says, hey, I want to add 5 minutes, thank you. I want to add all of V8 plus the first element of V12 and put the result in V4. Okay, fine. In Elmol 4, unfortunately, now you want to add all the numbers in V8, V9, V10, and V11, which makes it a little bit more difficult to break it into UOPs. Not impossible, but just a little bit more difficult, right? So you'll either have to express that as, some weird instruction that has not one source or 2 sources, but 6 or 10 sources, which is annoying. Or you'll have to have a temporal microarchitectural register or something like that, and then deal with the complications that you cannot take interrupts in the middle of doing that, right? So there's extra stuff. VR gather is a little bit even more difficult because VR gather, which is a really powerful instruction, it's saying that, a VR gather says, if you're in Elmol 4, you're saying that V8, V9, V10, and V11 are a gigantic vector, and that V12 has pointers or indices into this vector anywhere in the vector, right? So the first microop that arrives into the execution unit could want the last element on this gigantic vector. And that's a bit of a problem because then the first UOP that arrives to your unit needs all the sources renamed. So again, it's one of those problems where you'll get the UOP needing lots of sources, right? And you have to deal with that. So it doesn't quite work, and you'll have to deal with that. I hope I struck the right tone. I don't want to discourage anyone from building this. It can be built. We've built one, so we're very happy. I'm just, wanted to share with you our experience in that it's going to cause you a lot of extra stuff, right? It's, I'll put a picture. It's a little bit more fun than me just talking. We have our out-of-order core. It does do full renaming. You see the rename stage there in the center. I'm not going to bore you going you through the thing. There's 3 queue, the memory issue queue, the global issue queue, and the vector floating point issue queue, and everything is renamed, and all these annoying issues that I've described have been dealt with, and it can be done. But however, it is far more difficult than the Inorder version of the same thing. So we also have an Inorder version of this, and it's frankly far more simple than the out of order one. So if you want to join us in the fun of going out of order, please do. Or maybe you want to license it from us in case you're interested. And with that, I think, what is the time? I'm done ready for questions. Thank you very much. No one here? Please.
So Andreas Koch, TU Darmstadt. Truly heroic work you've been doing there. And I know you have been at this for quite a while. I have lost a bit track of the discussions in the vector group, so this is a more generic question than out of order vector. What I have observed in a number of projects I have been involved with and talking to other partners, both from industry as well as academia, many people say RISC-V vector 1.0 is too complicated for them to consider. So many of them just do some cherry picking, pick and choose. This set of instructions works nice for our use case. That set of instructions works nice for that use case. Are you aware of any efforts to unify subsets of RVV 1.0 so that a compiler more easily knows what is actually available in the hardware?
Oh boy, that's a really good question, but very tough. Let's see. As a vendor, I'm now happy because if the other ones don't dare to do it, I hope they'll come and license from us. So as the member of the spec group, it is a bit complicated, but the software people are actually happy. So the compiler people, there's a lot of work happening at Sci5 and also I know at BSC. The compilers are actually pretty happy with all that the ISA is giving them, so they're actually taking advantage.
I'm talking about hardware people.
No, I know, but it's the compiler is more important than our suffering, right? So if the compiler people are happy, a little bit extra suffering in the hardware is the right thing to do. You always have to favor the software ecosystem over the hardware happiness, right? So if the compiler is there, then implementing the full spec is in your advantage. I understand someone could say, oh my God, the segmented loads make you spin your head, fine, or the first find first and stuff like that. But the compiler is using it, so you're going to find yourself with an ecosystem that expects LLVM to just generate that code. If your VPU doesn't do the 1.0, you're going to be in trouble. So I understand the feeling. It is a little bit daunting. I don't disagree, and maybe a few tutorials would help. But it's a really good thing to do the full spec. You put yourself in a weird niche if you only do VAD, VOR, and VAM, so to speak.
Okay, thanks for the opinion.
One more question. How many man years did it take to build and verify an out-of-order vector unit?
Oh, well. Can I pass on the question? Let me not answer that one. Many, lots of those. Yeah. Actually, verification is very tricky, especially vector loads. Anything vector memory with the exceptions, interrupts, and vstart is also very difficult. I didn't even talk about vstart, but vstart is very difficult. So I appreciate the question. Sorry, I don't want to answer it, but yeah, it's a good one.
Alex Solomaitenko, Sci5. So can you comment on performance of your VR gather implementation and segment loads and stores?
On VR Gather, we have this big table for SEW and Elmol that I do not have in my head. So we're happy to share that with people that care. Our VR Gather, scales. The fastest ones are the medium-sized ones. We've optimized for 16-bit and 32 bits. 64-bit is a little bit less optimal, and 8-bit, we don't have enough bandwidth to write all the possible 8 bits into our vector register file. So there's like a little bit of a performance like that. And your second question was on the vector segmented loads? No. The segmented loads, we do maximum one address per cycle. That's our, so we generate whether it be it, now that address, if there's multiple data in the cache line represented by address, we get all the data at once from that cache line. So, if you want to think about it, to unify all the performance in our machine, the vector loads, vector gathers, vector strides, and vector segmented loads, they'll look at the address and say, okay, how many useful bits can I get out of this current cache line? Generate that, and then go to the next cache line. That's how we do it. No, we're limited on the vector register file. We're limited to the number of ports we have. So there's a limit. There's two limits: is how much data you get from a cache line, and how much we can write into our vector register file.
Oh, sorry, we don't have time for any more questions.
I'll be happy to take questions in the break. So, thank you very much.